I will ask her to then. And then if we both do it, she'll probably get obliged, so.
Probably like, hey, so we're both a bunch of lazy bums and didn't do our homework on time. Can we?
Yeah, or at the very least, move it to Friday morning instead of, or Friday night instead, or next
Friday,
night.
Saturday, Sunday, yeah. It also depends when she gives us her test.
She hasn't written it yet.
Yeah. So.
I just talked to her about it yesterday, so.
Yeah.
She's not for sure she's gonna have the whole thing take home or just a portion of it.
I hope the whole thing's take home.
She's thinking, she's not for sure yet.
Mm.
I was like, so you're gonna have pair of those things.
All right. I thought about it right after we ended lecture last time. There was a minor mistake right at the end of that last problem. I was rushing too much. So we added the add 0 here on this. This is the very last problem. And then when we have our form here, when we bring this -2 over, what do we need to do? Because that's the -2 from right here.
Subtract them from both sides, or have them negative.
Nope, we're just simplifying. This -2 is associated with
11/5, so you gotta multiply that through.
Yeah, so you just got to bring that through. I was like, that's the important part. So that brings it through, and it only changes this, right? So what do we have? +22, so -2/5. Changes this guy down here. Just as an FYI, just wanted to make that clear. That is the big thing. All right, we're bringing that over. We got to make sure that you carry. All right, it's all about just identifying what those coefficients are. Okay, so far in Laplace transforms, and actually even a little bit past this, we haven't done anything that like we couldn't have solved another way. Where Laplace transforms really, really shine are step functions or Heaviside functions. So a step function, basic switch, right? It's off at the point C and then it turns on, right, at the point C. Now, the notation we're going to use, all right, U of C, where C represents this point, okay? This is not the same as the complementary solution that we've been looking at, okay? So this is our standard notation for Heaviside functions, all right? And we're going to turn our step functions into these because then it works a little bit better with Laplace transforms. As a couple of notes, some other notations. Without a doubt, this first one, U subscript of C of T, all right? That's the one we're going to use, but you also see it as T minus C or H of T minus C because it's saying the function is shifted. That's dependent upon where this is happening, all right? The nice thing about these is that the coefficients, I can multiply by 4 or -7. And so instead of going up to 1, right, it goes up to 4 or it goes down to -7. Similarly, 1 minus this function means the function is on and then turns off at point C, right? So it goes from 1 to 0. Similarly, then I could multiply it by a number. Oh, look, multiplied by 3, the function is on at 3. And then at point C, it turns off. That's the whole idea of, right, what a step function or Heaviside function is. We can adjust this to be more complicated functions because you'll simply just multiply it by this step function that is an on-off switch at the point C. Turning these step functions into Heaviside functions is something we want to make sure we know how to do. All right, so I have my function f of t, right, and I have it written as a piecewise, which we're very familiar with. But I want to practice the Heaviside notation. So the function starts, all right, it is at -4. It sits there and it runs at -4 forever. Then, all right, at the point 6, So this is our new notation, U of 6 of t. Okay, it changes from -4 to 25. So the only thing we really need to figure out is how do you get from -4 to 25? And that's simply just the difference. So what's the difference?
21.
Not just subtracting, but if I'm down at -4 and I go up to 25,
Oh, 29.
29. Yeah. And so the simple way to do it, 25 minus the previous value, -4, which would give us 29. So I need to go up 29 spots. And this actually, right, even though it says plus 29, this puts me at 25. Then same thing. And I could write all of these out initially. U of 8t, okay, because now we're changing. And it's 16 minus 25, which is -9, right? Because by definition, to get to 25 to 16, just subtract 9. I was like, the easy thing is just to subtract it, but you can do that in your head as well. Just writing it out for completion here. And then lastly, 10 minus 16, which gives us -6. And this happens at 30. So even though notice these values are not the values, right? Because it starts at -4, goes up 29, so -4 plus 29 makes 25. 25 minus 9 makes 16, right? 16 minus 6 makes 10. So that's actually how we're going to be writing out. This is the same equivalency, all right, as our typical piecewise functions that we're most familiar with in our new notation. So this was just on-offs. Notice that we were going to a fixed value on all these. But this works for functions, right? So if I have this function f of t and it looks like whatever, all right, I can turn this into a heavy side on-off switch. The whole idea is that I just shift the function, right, by t minus c, t minus 9, whatever that point is. The function is then off, and at the point C, turns on, and notice, right, this is the exact same graph. Then it becomes that function at that point. So you can adjust this and make lots of different functions, turning on and off, or becoming a particular function for a particular range of numbers. The most important part about this is that with Heaviside notation, all right, we're going to make sure, all right, we have the function has to be of the form t minus that number, all right, and then we have the Heaviside function attached to it, and that becomes the function that we're going to adjust and create. So for Laplace transforms, we have various values and just some light proofs using the definition, but again, all right, notice, right, we have our negative st, which we started in. We put our function in that is adjusted, okay, and it basically solves out that every time boils down to essentially the whole idea is that negative, the Heaviside equation boils out to -c, whatever that number was, of s. All right, this is for 1, right? And so typically, remember with just Laplace transform of 1, it equals 1 over s. So this is the Heaviside function, oh look, times 1 over s. So just whatever the function is, when you do the Laplace transform of it, it's e to the negative value, all right? And then 1 over s. And so whatever adjustment we have, you can basically can pull out the Heaviside, and this is why, right, we pick the natural number as the Laplace transform for the Heaviside function, all right, because this is going to be an easy one. And then whatever the function is, we'll just have to mess with it in order to identify how that part transitions. Just as a note, all right, in our table, Heaviside functions basically 25 through 29. So all of these are the Heaviside equivalents, but most of the cases we're going to work with 25 and 27 because This is the Laplace transform of just a heavy side, and this is the Laplace transform with a function. And notice the transition. As long as it has the form t minus c, it transitions to just, all right, s. Notice that it doesn't have to be s minus c over here. All right, we're going to see some examples of how this works, of course. So, again, let's look at some examples and see if we can break these down. All right, let's do the Laplace transforms, and then we're going to do some inverse Laplace transforms. So forwards and backwards. And I want to emphasize, that's the biggest part. So we're gonna see this, right, even in this first one. All right, so if we have the Laplace transform 10, so just one piece at a time because of linearity. So this becomes 10 of the heaviside function at 12. GS. Okay, so the first one, this is exactly 25. Okay, this becomes e to the negative, right? 25 with c equals 12. E to the negative 12s times 1 over s. That's the simple case. All right, I have basically the Laplace transform of the heaviside function, which is e to the negative cs, and then 1 over s because I'm the Laplace transform of 1. All right, but basically every time you have a heaviside, and I can identify that already, right? I have e to the negative 6s, e to the negative 4s. So these other two are basically combos of 27. But, all right, we're going to pull those apart one piece at a time. Actually, let's separate this out. Let's call this one K of S, and let's go this one is W of S. Or technically at this point it's T, K of T. So the big thing, all right, is the form, right? This is in the proper form. This has to be in the form of t minus, in this case, 6, u of 6t. Because at this point, my c is 6, which means the actual function here, what is this equation? If that is f of t minus 6, right? F of t minus 6 equals t minus 6 cubed. So what's f of t? What would the original function be if it wasn't shifted?
T cubed.
Yeah, it's just t cubed. All right. And that's the big thing, is identifying that, okay, I have this. Well, now that I have f of t, which is just t cubed, I can then identify what the transform will be. And what number is this?
7.
No, not just this.
Number 3.
Yeah, 3. You're absolutely correct. Overall, we're dealing with number 27. All right. But just f of t is t cubed, all right? Since that's number 3, right? With n equals 3. So that gives us what? 3 factorial all over 4. That's the 4. Because when this transitions, so once I get k of s, since this is 27 overall, this piece I can dump out e to the negative 6s, and you don't, right, bring this adjustment over. So we're going to see this in a Laplace in inverse transforms. This just then becomes, because this is always going to be k of s equals f of s times e to the negative cs. That is what number 27 says. It says, do your transform of the function, all right, and multiply it by the Heaviside transformation. And so then, yes, so it's the 6 over s to the 4th. And so identifying this piece, right, and then creating the initial unadjusted, unshifted function, that actually, all right, is the transform of that. All right, let's do W. Then we'll put it all back together. So W of t. So yes, again, it's 27, but it's always good to break down and identify that. So my t minus 4 function now, right? How do I know it's 4?
Because the constant's 4 for the u.
Yeah, because the Heaviside tells me what number I need to make sure I have to pull out. Because I already have part of it, right? W of s is something times e to the negative 4s. So I've got that part. Now I'm just finding the piecing here. Okay, so f of t minus 4 is then 7 minus e to the 12 minus 3t. Now, good news. The constant right here, guess what happens to that?
Goes away.
Well, goes away. It's strong. Like, if it's a constant times the Heaviside function, the Laplace transform of this is just what?
1 over s.
1 over s. So that one, oh, good. So really, I just need to kind of work with the other one. 7 minus e to the, so what do I need to pull out? Because I need this in the form t minus 4.
Pull out 4.
Pull out a 4?
Or I guess pull out 3, I guess, sorry.
Pull out a 3. Okay, if I pull out a 3, I get that. Okay, looking better. Let's pull out a negative 3. 7e. Negative 3 gets me t minus 4. Now I have the correct form, which means f of t is 7 minus e to the negative 3t. Once I get rid of the adjustment. And this guy we already identified, right? That's number 1. And what's this guy? Number 2. So then, all right, you can just do it piece at a time, right? So number 1 and number 2. And then the adjustment, so this becomes 7 all over s minus 1 all over s plus 3. All right, and then we can put all the pieces back together. So we have a negative and a 2, all right, to put it all together. So my g of s all the way out. And this became a 12 because I had a 2 above it. We had just done the function inside. But basically, that's how we transition heavy side functions. When we put them back, as we're going to see, notice that we're adjusting, right, the unshifted function. So when you put it back, you have to put that t minus 4, t minus 6 back into the equation. This says that this is a heavy side. And it's always going to do that. Notice, right, in our table, all these adjustments that we had, all these transforms. Notice what's not here on the transform side, e's. If you have an e in your function, that means you did heavy side transformations. All right, so that's actually good news for us. We reserved, right, the natural number, the natural function, all right, for the most complicated types of transforms. Because even when we start, we have e's here, we transform it into a fraction. Okay.
And again, this is like I said, this is where the Laplace transform really shine.
Okay. Okay, before we do the Laplace transform of this, we need to transform this into a heavy side function. All right, simple step functions. All right, a lot of this is how they tend to look on-off switch. So basically, we start at t to the 4th. So the function is t to the 4th, and then, all right, this minus this with u of 5 of t. But here's the good part. Oh, look, t to the 4th minus this guy. So the second function is just this piece. So, what's that f? Equals t to the 4th plus 3 sine t 10 minus 1/2 u of 5t. So just creating, all right, our function. Now I want to do the Laplace transform of this guy. So the first one should be pretty easy, all right? That is just number 3 with 4m equals 4. The second one, all right, clearly number 27. All right, but we have some adjustments to make. So the Laplace, the heavy side always comes out. I got e to the negative 5s for that guy. In order to make sure I have the right form, what should I attempt to pull out here?
1/2.
Okay, pull out a half.
Oh, 10, so the t's on its own.
Which might be more helpful, right? We pull out 1/10, right? The first piece is t. What's the second piece?
1/20th? No, 1/5 or 5.
Ah, it's just 5, right? Because yeah, all you have to do is just you divide by 1/10, whatever you factor out. So look, 1/2 divided by 1/10 is 5. Oh, and it actually worked out. We now have our form, right? As we're always looking for, we have our function f of t minus 5 equals this thing. Which means f of t is actually sine of 1/10 t. And then, right, what number is this?
7.
Number 7 with A equals 110. So it's always making sure that you get back to the initial function. And this little process here, right? We're about to see a more difficult one. Notice these have factored really nice. That definitely doesn't happen. All right, so we're gonna see that in a minute. Okay. So just be aware, all right? But doing this process to make sure it lines up, right? Everything where you put the t in, all right, had a t minus 5, and then if I'm just doing f of t, right? Simple substitution, all right, of the variable. All right, so then this guy should become, let's see, a, right, say over. So 1/10 over s squared plus 110 squared. We've got our pieces and we can put it all together.
What's this?
With some algebra adjustment, we can make it in a prettier form. But this is actually, I was like, this is done, right? I was like, this just makes it nicer, but same. All right. F of t. So starts at t, then at u of 6. All right. What gets multiplied by the heaviside function?
E.
I just mean when we actually read it out.
U of 5.
F of t equals t plus u of 6t. And what's this piece? And I can put the heavy side. This you could, I know I've been putting the notation, yeah, but you can put it in the front too. So.
T minus 6 squared.
Say it one more time.
T minus 6 squared.
T minus 6 squared. That's not, we're missing some stuff still.
Minus 8.
Minus 8. Yeah, so okay. What have I been doing to make the rest of the function? When we did that first one, right? You got to step up because we started at the function t. And then I moved to this function. So how do you find the
If you have a difference, so T minus all that?
almost that minus t.
Okay.
So it's always the next function minus the previous function. So yes, all right. And that's the easiest way. That's why I was showing this right here. Because that concept just continues. I'm 25 minus 4, right? Minus -4. 16 minus 25, 10. You just take that function, subtract off the previous one every time. That's how you create this in heaviside notation. All right, so we have that function. Okay, let's write that. Class transform of f of t. Class transform of loss function of t. Okay, so first one, right? Piece of cake. Number 3. second one. Now here's the big part. Okay, so we have u to the 6. And again, let's call this guy. What are we on? How about z of t? Z of t. Actually, let's call this z of t minus 6. Just to make this. No, because I'm going to recall that. Darn it. Okay, z of t, and then we're going to call that other thing something else in a minute. Okay. Okay. Calling this thing W of t minus 6. All right. So again, I'm just making a lot of notation and it's all just means to an end. You don't have to do it this way. I just want to make sure we're keeping everything clear. So this needs to be t minus 6s. I got one. Okay. This is the other guy. Now there's a couple of ways to do this. All right, but once again, I need this. I can't just have a t. This needs to be a t minus 6. Okay. I could bring this in and mess with that, but let's just leave that over because it's constant. So in order to get t minus 6 here, what do I have to do?
Add 0.
Add 0 every time, right? Continues to be that same concept. So I got -8, that's over here. I got plus t minus 6 squared, that one's good. So this guy, negative, all right, I'm gonna keep that negative there, t minus 6, t plus 6. So I'm gonna add 0, all right, to t, and then, okay, so then -8, this becomes negative t minus 6 there, and then the plus comes out, but actually becomes negative again. T minus 6 squared. Which now, okay, so what do we have? -14 minus t minus 6 plus t minus 6 squared. All right, and I wanted to add 0 to emphasize, because even though I have that 8, you don't always have a number that's above the number you need type thing. Then I can actually identify what is my real function. What is w of t? When I get rid of the t minus 6 adjustment.
Just t squared.
T squared minus 14, almost.
Minus t.
Minus t. I was like, we wrote that in descending order, right? We just flipped that. But yeah, this is actually just t squared minus t minus 14. It's a simple quadratic, all right? And AKA is really just number 3 and number 1. All right, so that's the whole idea, all right? Getting that into the correct form, this is where the work of the heavy side comes in. But it's still just algebra, adding 0, multiplying by 1s.
Why can't we distribute the t minus 6 and then, you know, like factor all that?
Oh, I could, but every time, but wherever I would end up with just, so when I do that, I would get a t squared, right? A singular t squared. And I have to.
The same problem again. You
I'd
gotta
have to add,
do this again.
I'd have to add a 0 in there. But you could
Okay.
multiply it all out, simplify it, and then do it, and you would end up with the same thing.
Okay.
I was like, that if you already have something that's adjusted, I wouldn't
Don't break it down.
Yeah, I wouldn't multiply it, like FOIL it out to
Okay.
then have to do it
All over
this
again.
step later.
Yes, sir. Okay.
I was like, okay, so, and then this guy, yes, so then W of S will actually become 2 factorial all over S cubed minus 1 factorial all over S squared minus 14 all over S. Then we can multiply that guy into our Heaviside function.
Z of S.
Yeah, our Z of S, because there's W of S. And then that other one was number 3. It should be basic again. So F of S equals 1 over S squared plus 2 over S cubed, like we just had, minus 1 over S squared minus 14 over S times e to the negative 6s. Very, very nice. All right. Okay. We have to go forwards and backwards. Now, the good news is, actually, it's a little easier from this side. Inverse Laplace transforms, because I can recognize, are these Heaviside functions?
No.
Yes.
Okay, because they have E in them.
They have. We're on the other side now. We're
Okay.
on the S's.
Okay.
Okay. So on the function side,
UE.
we have T's and we have the U's, right? U of 6T. Okay. This time we're starting with S's and we're going to our original variable, the variable of the problem. Remember Laplace transform? The whole point of it is a means to an end. So we have to do transforms, you solve it, then you do inverse transforms, all right? And that's what we're going to look at next week. Okay, so I know these are all Heaviside functions because I have E's in my Laplace transforms, which means all I have to do is separate out all right, my Heaviside function, and I know, all right, that then I just need to solve that function. We already talked about this a little bit. So I can ignore the Heaviside function. I'll bring that back at the end. I need to do the inverse Laplace transform. This guy, what do we do? What's the technique we refreshed on and we love?
Separation of partial fractions.
Partial fractions, right? It's simply just partial fractions. So this actually can break down. And then what's the other method? What method do we need to use? Cover up method. All right, so let's see, S equals negative 2/3 on that one, S equals 2 on that one, cover up, solve it in. Did that for us. I'll write that out just to negative 2/3, S equals 2. And look, 1/4 positive, they're both positive 1/4, right? You had said something that they summed to 1, or right? Yeah, it was like pure coincidence,
Okay.
right? I was like, this case they summed to half. And I was like, sum to 0. What? It's just whatever you plug the numbers in to be. Okay, and this is currently H of S. So let's call this guy F of S. And then just to clean up our form a little bit. Both of these look like what?
$17? No. Not seven.
Two.
Yeah, the two. Yeah, I was like, don't overcomplicate it. How do I know these aren't basically anything from 7 to, yeah, I don't know, 22?
Because yes is not square.
Yeah, it's not square. Just remember, just give the denominator a quick look. That guy's dead on. What do we need to do to this one? Pull a 3 out. So let's see, 1/12. This becomes 1/12, 1 all over S. I'm gonna write minus minus 2/3 plus 1/4, 1 all over S minus 2. That's already in the correct form, which means that then we can just do both number 3 with different A's. All right, so here's the important part. Inverse Laplace transform, this equal gives us f of t, which becomes 1/12 e to the negative 2/3 t plus 1/4 e to the 2t. Always watch those signs, those negatives always get me. Okay, so I was calling this whole thing, all right, f of s. So what I had is h of s equals f of s e to the negative, I already lost what the number was, 4. So we have a Heaviside function. That means h of t has to be f of t minus 4 u of 4t. So, right, Heaviside function. So you deal with that function f of s just like we convert the other way. I found f of t. So what do I need to do to that to complete this?
Shift it,
Yes, by doing what?
adding or subtracting 4.
No. F of t is this, but I need f of t minus 4. So the opposite of what we just did in the previous problems. We kept factoring out.
Make a home function, find the home function or find the,
Multiply it in.
It's not a multiply. It's a substitute. We were undoing it, right? So if I have a t, wherever there's a t, what do I need to put there?
minus 4,
T minus 4. It's even easier. It's not a multiply. It's literally.
plug a chug.
Yeah, this is f of t.
Oh my gosh.
I need f of t minus 4, which means wherever there's a t in your function, just put t minus 4 in. So it's even easier than you guys were thinking it was complicated. But it's important because we just spent all those other problems pulling that t minus 4 out. So thank goodness on this side, all you got to do is just replace it in. So u of 4t, then this whole thing becomes 1/12 e to the negative 2/3 t minus 4 plus 1/4 e to the 2 t minus 4. Now beware, feel free to, you can multiply that to negative 2/3 in, but this is a better form because why?
It's already in the T minus, like the,
Yeah, it's already,
the shifted form.
it's already factored out, and this is indicating, it's a Heaviside function that is adjusted, right? When you multiply it in, we had to do all that crap we did above, where we had to pull it all out. So leaving it in this form is actually the better form. Okay, G of S, so let's write this guy out. All right, so we have two heavy side functions here. Be aware, very much, what seems to make the most sense, do this. At least initially, this is what I would do. Just because I'm trying to organize it, I got two different heavy sides, right? Here's the important part. In order to solve this, what do I need to do?
Partial fractions.
Partial fractions. In order to do this, what do I need to do?
Partial fractions.
They look pretty close. But, all right, the partial fractions are distinct on both of them because of why?
Distinct function, distinct coefficients.
Nope. I would solve this one as a partial fraction. I would solve this one as a partial fraction. What makes these two different partial fractions versus the exact same partial fraction?
The numerators?
Yeah, literally just the numerators.
Okay.
So if we actually decide, how about this? How many partial fractions do I have to do now? And so this is an important thing to identify because with heaviside functions, we're going to be doing a lot of partial fractions. So you want to reduce the work wherever you can. All right. And it's super tempting to do this, but this, you would actually end up, this will break down into, we're going to have to break this into, this will be three coefficients. These three coefficients would be different than these three coefficients. It would all work out, but you just doubled your work. So this way I only have to do one partial fraction. And here's the important thing. I'm going to do partial fractions. Is this cover-up method?
No, we have to use a matrix.
No. Why is it not cover-up method?
Squared.
How squared?
Yeah.
That's the big thing. Remember with cover-up method, we're able to completely factor our function apart. First degrees only. Soon as you have a second degree, you have stuff in, remember we have the BS, B or AS plus C or BS plus D, but it doesn't matter, whatever it is, right? So you have to be able to completely factor everything apart in order to use cover-up method, which is our super fast way, right? If you can't reduce it down to that, then, all right, and that means that's its individual matrix, that's an individual matrix if I do these separately. And the only thing differentiating them is a 5 and a 3, but it makes for distinct matrices. Okay, once again, all right, so I'm going to call this thing, I have something f of s, and then I have some heavy sides. And basically, this is how you approach it every time. I got heavy side stuff, and then I have the work here. All right, so our f of s function is this guy 1 over s plus 2, s squared minus 9. Now we can partial fraction this. I don't want to use the same number. I didn't use it for that one. And this is bs plus c all over s squared plus 9. All right, and again, simple common algebra stuff, right? Is this factor? No. This is a sum of squares. This does not factor. This is not s plus 3 times s plus 3. Just profession. All right. Because your partial fraction becomes a mess. Also, that does remind me. If you have something like, if this was s squared minus 9, s squared minus 9 would factor, right? You cannot do this. Oh. Partial fractions won't work. Partial fractions only work if everything is completely factored. Okay, so just be aware of that. I was like, I've seen that because your coefficients start like messing up because you added a numerator and then you added a variable in the numerator. You didn't need one. So make sure you completely factor your denominators before you break it into partial fractions. Okay. And then, yes, now matrix all the way. Let's see, multiply this guy by s plus 2 times s squared plus 9 all over 1, entire thing. This then becomes 1 equals. There's 4. Once we got our matrices, should be all good. And it says they're all 113, so I'm gonna pull that all the way out of our FFS function. This is 1 over s plus 2 plus negative s plus 2. All right, so the first one, piece of cake. What about the second guy? This is clearly number 2. What's the second guy look like?
A lot of them.
But primarily, which one should be jumping? Which ones should be jumping around?
Oh. 17 through, no, yeah. 17, 18. Or, where's the other one? 7 or 8.
7 or 8. Yes. 17, 18. Yes, it's in that neighborhood, but because it's positive, same thing. So 17, 18 gets you on the right track, and then just double check. So yes, we're looking at 7 and 8, which means break it into its pieces. And then this guy, s all over s squared plus 9, that now looks exactly like number 8. Number 8, it might as well with a equals negative 2. And this guy is with a equals 3. This is now number 7 with a equals 3. But I need to make this most minor adjustment, which is on the very last one here. And I could make this more clear.
The A has to be up top.
Okay, I have to get the A up top, so I'm gonna pull that 2 to the front, which means how do I get the A on top?
Multiply by 9.
Over 9. By 1.
Multiply by 1, and I'm not multiplying by 9.
It's 3 over 3.
Yeah. It's 3 over. I was like, it's not a 9, right? I was like, I didn't write the
I see.
A squared.
Yeah.
Yeah. Just multiply by 3 over 3. I kind of skipped that step, but hey, in the beginning, make sure I was like s squared plus 3 squared to make sure you are clear, all right, with what your terms are. That's also why I'm always writing these, just to like tell myself it's a 3. That's actually a 3. All right. So I was like, it does not hurt to do this over and over because I keep going back and forth because eventually you start like memorizing and seeing these, right? But I was like, Laplace transform is just beautiful. Okay, all right, so let's do our inverse. And notice, we haven't messed with that heavy side at all. We're doing all this with the function. Just the piece, all right, the main function. Okay, so this whole thing is by 1/13. Can't forget that guy. I want to bring that back in now. Maybe in a minute. E -2t minus cosine 2 plus 2/3 Okay, so we got that guy transitioned all the way back to our function, all right, f of t. But we got to go back to our g of s, which means, all right, g of t equals, now good news, 5e, actually let's write this out in this station, we'll do one last one, 5u, u of 6t f of t minus 6 minus 3u of 11 t f of t minus
6.
11. This one's 11, right? Because
Yeah.
it just pairs with whichever one is there. All right, so to write it all the way out. Now again, the good news, oh, there's my functions. Everywhere where I have a t, I need to put in either a t minus 6 for this guy or a t minus 11. Are you with me?
Kind of what, does it matter which one you pick? T
Oh,
minus 6 or T minus 11? Like,
well, that function is going all the way in here with t minus 6, then it's going into this one. So it's we're about to write a big long thing, but we'll make sure everyone's with me. I was like, that's why I kind of like to write this stage, just to make sure I'm keeping track, because I got my whole function. Now I got to put in a bunch of replacements. All right, so finally. G of t. Oh, you know what? 1/13th, while I'm at it, let's make our lives slightly easier. 5/13. Beautiful. Right? One has the t minus 11s, the other has the t minus 6 because it goes with each of the Heaviside functions. All right. Okay, This one, I wrote all the way out for you because I want to just point out some things because these continue to just be more and more algebra. But sometimes it's the first steps. So once again, looking at this, pair your functions, all right, with what your partial fractions are going to be easiest. 3s, 8, again, ignoring the heavy side pieces, 2s, 6. The best way to pair these together, I'm pulling the s's together and I'm pulling the constants together. Doesn't matter that there's some heavy sides and some not, because we've seen how easy the heavy side function is actually to deal with. You pull it away and we just deal with the partial fraction stuff. All right, the heavy side is basically the easiest part of this. All right, the partial fraction is where all our algebra and time go into. Also, this emphasizes. So if I have this one, notice I had an s in the numerator here. If I have s squared, that cancels. So notice this one, you have to do two different partial fractions. But versus 4, I can reduce this to 2 partial fractions instead of 4 partial fractions. And notice this one, s times s plus 3. Guess what I get to do on that one? What method?
Cover up.
Cover up. This guy's cover up. S squared, no. Okay? But I was able to simplify this from 4 annoying partial fractions to 2 partial fractions and only 1 painful one. And that's what I want you guys, like, because we are solving, and what we're going to eventually do is we're going to solve IVPs, high order IVPs next week with step functions, stuff that takes very high level calculus. What are we solving this with? What are we solving all these with?
Algebra.
Algebra. We're solving crazy complicated equations with algebra. I was like, that's why Laplace transforms, like, this is where they shine. Because like, it's like a nightmare to solve these with calculus. But with this little transformation, and Fourier transforms are similar, you turn these crazy things. Now, is the algebra sweet and beautiful and clean? No, it's messy. Okay, and you have to focus, but it's still algebra. I was like, we're solving crazy hard problems with algebra, and that's why I love DFQ and why I love Laplace transforms. All right, so use some partial fractions on that first one. You do cover up, and notice how we have it written here, exactly what we just did on that last problem. All right, I can do cover up on one of them. All right. And I can do, then we have the matrix on the other. We solve it down. All right. And you get it to this thing, okay, where I identified my f of t's and t minus 3's, where I have f of t and h of t. And then just to make sure, let's write this out all the way. So I didn't do the very last step for us, just so we can do it. All right, because I always want to make sure we're practiced with this. So our function g of t, all right, is this whole thing where I have f of t as this guy and h of t of this guy, right? So when you put f of t minus 3, that means, what am I doing to this?
Making that t minus 3.
Yeah, making that t minus 3. All right, so let's write this guy out, all of them. But it's basically it's the exact same as our last question. I just wanted to emphasize, all right, approach. So Beautiful. Deep breath. But it just, it's like, looks beautiful. I don't know, something about it. All right, so that is all I wanted to get through today. Just want to make sure, all right, next time next week, we are finally actually going to look at the really, really good stuff, which is forwards and backwards. All right, so we've been doing the Laplace transforms forward, we're doing them backwards separately. Well, in order to solve an IVP, you have to do both. It's okay, just good. Deep breath.
I thought